Good evening, dear students. So today we will learn variance and standard deviation. If you recall, dear students, in the last class, we discussed about the limitation of mean deviation. And during that class, I said at the end of it that that those limitations, okay, uh, you know, motivates us to learn a new concept of standard deviation, that another method of dispersion or another measure of dispersion, I can say. Now, before I proceed further, please confirm that you are able to hear my voice very clearly and able to view the screen properly, dear students.
Yes, sir.
Yes, sir.
Okay, great, thank you. Now, before we start variance and standard deviation, let's revisit whatever we have, uh, learned in the, mean deviation. So the fundamentals of mean deviation. So what is that? While calculating mean deviations about mean or median, okay, one thing we have noticed that the absolute value of the deviations were taken, correct? That you remember that mod of xi minus x. That is the absolute value of the taken. The absolute values were taken to give meaning to the mean deviation. Otherwise, the deviation may cancel themselves by means of positive value and negative value. For example, for some data, we get mod of xi, you get that xi minus x bar, xi minus x is equal to, we get 5. And for another data, for example, xj minus x, we get minus 5. Then if we add these two, we get plus minus 5 got 0. And to eradicate that one, what we considered is that the absolute value. So that mod of 5 become 5, but mod of minus 5 is also 5. So when we add that, then we get what? We get 10. So this is a difficulty. This is not the right way of doing. So another way of overcome this difficulty, which arose due to the sign of deviations, is to take squares of all the deviations. One method is that take the absolute value, and another one is that take the squares, because we know the squares of a negative number is also a positive number. So that means what? That means if we can do something like this, let me first place that note in front of you, and after that I will explain. So what is this, dear students? So here we say that another way of overcome this difficulty, which arose due to the sign of deviation, is to take squares of all the deviations. Obviously, all these squares of deviations are non-negative. So for example, if x1, x2, x3 up to xn, be in observation with x bar as the mean, then we derive the value xi minus x bar whole square for I equal to 1, 2, 3 up to n, get the following. So what we get? We get this, summation. x1 minus x bar whole square plus x2 minus x bar whole square plus x3 minus x bar whole square. In that way, we get, so the, xn minus x bar whole square. So that is equal to summation of, so ideally there should be some dot dot plus here. Okay. And that is equal to summation of I equal to 1 to n xi minus x bar whole square. Now, dear students, there are some important observations. What is those observations? So let us first, let me first place the note and then let me explain. So now, based on the value of summation I equal to 1 to n xi minus x bar whole square, we can conclude the following related to dispersion. First one, if this summation of I equal to 1 to n xi minus x bar whole square is 0, then the conclusion is that the observations x1, x2, x3 up to xn are exactly equal to the mean x bar, and therefore there is no dispersion at all. Correct? Now, if this summation I equal to 1 to n xi minus x bar whole square is small, then the conclusion is that the observations x1, x2, x3 up to xn are close to the mean x bar, and therefore there is a lower degree of dispersion. And lastly, if the summation I equal to 1 to n xi minus x bar whole square is large, then the conclusion is that there is a higher degree of dispersion. Then what we can say, dear students, that we can say, or I can place that statement in front of a question. So the question is, can we say that the sum I equal to 1 to n xi minus x bar whole square is a proper indicator of the degree of dispersion or scatter? Okay. You may say, you may think, yes, based on the statement what I've given. But actually it is no. And why it is no, let us understand by means of some real illustration. Okay, what is that for? So let me first place the statement in front of you, dear students, and after that let me explain. So as I was telling, that apparently it looks like this summation, that summation I equal to 1 to n xi minus x bar whole square is a proper indicator of the degree of dispersion or not. So answer is no, but why it is no, we should have a proper justification to say before no, before we say no. So that's why we took two data set. Data set A is containing the numbers 5, 15, 25, 35, 45, 55, and data set B, it contains this number 15, 16, 17, like this up to 45. So what we are going to do, dear students, is that we are going to compute the value of this summation xi minus x bar whole square for these two data sets. Now if we find this one, and you can also do along with me. So the deviation, okay, so we define this as a dA and dB. So if you look into this, and we need to find x bar, because to compute xi minus x bar whole square, so we need to compute x bar, right? That x bar we need to compute. So if you look into this, for both this data set, the value of x bar is actually 30. Okay, for both these data sets, that value of the mean is 30. So then what we can compute? So we compute, let me first write it down here, dear students. So now the point is that by means of these two data sets, we will experiment that the sum I equal to 1 to n just a minute. So by means of these two data sets, we will experiment that the sum I equal to 1 to n xi minus x bar whole square alone is not a proper indicator of the degree of dispersion or scatter. Now, as I already said, that mean of both these two data sets is 30. So now let dA and dB be the sum of the squares of the deviations from x bar of the observation of dataset A and dataset B respectively. Then, dear students, how you are going to compute dA and dB? So we are going to compute dA and dB something like this. Correct, dear students? So this is the way we can compute dA and dB. So now, sorry. So we compute the value of dA is equal to 1750, and we compute the value of dB is equal to 2480. And how you compute that is very simple. All these values are subtracted from the mean, that is 30, and then we made a square, and then after that we add all these numbers. Now, if you look into these two values, dA and dB, which are 1750 and 2480 respectively, so if you just look into these two, data set, that dA is less than dB. What we see from here, dA is less than dB. So what it says that dA is less than dB means that the observation in the data set A is less dispersed than the observation in the data set B. Correct or not? Okay, but this is what we can conclude by looking into the numbers. This we can conclude by looking into the numbers. So if you look into the equation 1 and 2, we get dA is less than dB, means we conclude that the observations in the dataset A is less dispersed than the observations in dataset B. That is the conclusion we are drawing by looking into the value of dA and dB. But dear students, if we plot the observation on both the dataset A and dataset B in the number line, we will get some other conclusion. And let me show you that how it will looks like if you plot into the dataset. If you plot into the dataset in the number line. Okay, so let me first plot it and let me explain further. So from the above equation 1 and 2, as I said, that we see that dA is less than dB means we conclude that the observations in the dataset A is less dispersed than the observation in dataset B. But if we plot the observations on both the dataset A and dataset B in number line, we will get some other conclusion. Here is the view once the observations are plotted in the number line. If you see the dataset B is actually like this, the values which are marked by cross, and in dataset A it is in the filled up circle. Now, what is that? If you look into the plot, we see that the dataset A of 6 observations has a higher dispersion about the mean than that of the dataset A of 31 observation, even though dA is less than dB. So what it says, the dA, that is the sum of the squares dA or dB, which represents that the sum of the squares of the difference of the values from its mean is not actually saying the exact fact. So which I wrote it here. So though dA is less than dB, okay, we see that the dataset A of 6 observation has a higher dispersion about the mean than that of the dataset A of 31 observations. So we just experienced that the sum I equal to 1 to n xi minus x bar whole square alone is not a proper indicator of the degree of dispersion or scatter. Now how to overcome that limitation? Now to overcome that limitation, we take the mean of the squares of these deviations. That is, whatever the summation we have explored so far, that is summation I equal to 1 to n xi minus x bar whole square, we divide it by n, the number of observations. And then we find something interesting result. Okay, so what is that interesting result? Let me first show it to you, and then let me explain further. So we just experienced that the sum I equal to 1 to n xi minus x bar is not alone a proper indicator of the degree of dispersion or scatter. To overcome this limitation, we take the mean of the squares of this deviation. That means that 1 by n into xi minus x bar whole square I is equal to 1 to n. And with this, we get the following. dA by 6 is equal to 1750 by 6, which is equal to 293.33. And dB by 31, that is equal to 2480 by 31 is equal to 18. Very interesting observation. Though dA is less than dB, but dA by 6 is greater than dB by 31. And it indicates that the scatter or dispersion is more in dataset A than the scatter or dispersion in dataset B, which confirms the number plotting of the above two sets, which we have done few minutes back. Correct, dear students? Here, the dA by 6 is greater than dB by 31, and dA by 6 greater than dB by 31 means the scattered nets in here is more. Here means this is more than this one, and which confirms that whatever we have plotted in the number line. So we consider that 1 by n summation I equal to 1 to n xi minus x bar whole square is as a quantity which leads to a proper measure of dispersion. This number, that is mean of the squares of the deviations from mean, is called the variance. That term is called the variance, and it is denoted by, sigma square, and the standard deviation is denoted by sigma. Okay, so you may wonder that, sir, variance is sigma square and standard deviation is sigma. Then why you introduce two different terms? Why not only standard deviation? Why is not only variance? I will explain that. If you have this question, I will explain it later. So based on the organization of data, that is ungrouped data or group data, the formula for computing variance, sigma square, and standard deviation, that is sigma, is different. And we are going to explore more on this. So I hope by this time you got a very clear idea that what is the motivation behind learning variance and standard deviation, right? Now, as you got that motivation to learn this thing, now we are going to see that exactly what formula we should use to find the variance and standard deviation for ungrouped data. And that I am going to explain in the next page. So let x1, x2, x3 up to xn are n observations of ungrouped data with x bar as the mean. Then the variance and standard deviation are denoted by means of this, following two, formula. So let me show it to you, dear students. So let x1, x2, x3 up to xn are n observations of ungrouped data with x bar as the mean. Then the variance is denoted by sigma square and is defined as sigma square is equal to 1 by n summation I equal to 1 to n xi minus x bar whole square. And standard deviation is denoted by sigma, which is nothing but the square root of whatever the previous value, that is square root of sigma square. So that means variance is sigma square, and what is sigma? Sigma is nothing but square root of sigma square. Obviously that we know. Okay. From the fundamental of laws of indices, we know this thing. So the point is that, so these are the two terms. Now let us see by means of an example. So, so let's take a set of a data set, not a set of data set. Let's take a data set as I mentioned below here. Let us understand by means of the following, by means of an example. Okay, so let us find the variance and standard deviation of the first 10 multiples of 3. What are the first 10 multiples of 3, dear students? It is here 3, 6, 9, 12, 18, 21, 24, 27, and 30. Let us form the following table towards computing variance and standard deviation of the given dataset. So what is the table we need to form, dear students? So we need to form a table something like this. Correct? I hope you understood the purpose of this table, because whatever the values you see is computed in different columns, especially the last column is meaningful. So, and we take a sum of all this, right? So how we compute? First, the data is given xi. We know the mean, that is 16.5. Means we computed the mean, the sum of all this data by number of data. Then we found xi minus x bar. Some are positive, some are negative. But the moment we make a square, all are positive, and then we found their sum, that is 742.50. Once we get this thing, dear students, then we get the variance and standard deviation by means of this simple formula. And that formula I'm going to place in front of you. So what we get, the standard variance sigma square is equal to 1 by 10 into 742.50, that is equal to 74.25. And sigma, that is standard deviation, is nothing but square root of 74.25, that is 8.62. So these are the values we got. So now let us find that how we can how we can compute the value of sigma square, that is variance, and standard deviation, that is sigma, for group data. And dear students, the group data are further classified into two categories. One is the discrete frequency distribution, and another is the continuous frequency distribution. So that we are going to learn now. And dear students, never hesitate to ask me any question if you have in between. Never hesitate. Okay. And more than asking question, what you need to do is that you need to make some real practice with examples and with exercise questions as available in the online platform at konarclasses.com. So now, as we know, the group data the group data is further classified into two categories. One is the discrete frequency distribution, and another one is that continuous frequency distribution. Okay. So how we compute the variance and standard deviation for discrete frequency distribution? So the way we can compute for the discrete frequency distribution is something like this. This actually all these portions, dear students, I took it from our study material. So so this section doesn't make much sense. 6.2.1 is not required. So this is the way we compute the variance and standard deviation for discrete frequency distribution. Okay. So discrete frequency distribution, that the values x1 comes with frequency f1, the value x2 with frequency f2, x3 with frequency f3, and in that way xn, the value xn comes with frequency fn. Then the variance we compute 1 by capital N into summation of fi into xi minus x bar whole square, and sigma is nothing but the square root of that expression, where capital N is equal to sum of all these frequencies. Correct? Now, this what we discussed is for the discrete frequency distribution. Now, let's find that variance and standard deviation for continuous frequency distribution. How we can perform the finding the value of variance and standard deviation for continuous frequency distribution. And for that, I'm going to explain you in the next page. So For continuous frequency distribution, okay, we need to follow the steps. The first step is that the given continuous frequency distribution is represented as a discrete frequency distribution by replacing each class by its midpoint. That is a step 1. Then step 2 is that applying these formulas. Okay, the moment we find that the midpoint value in the step 1, then step 2 is quite straightforward. And what is that? Here it is. And in step 2, what we are doing, so let me, yeah, that's fine. So in step 2, what we do, the variance and standard deviation is computed by the method as adopted in the case of discrete frequency distribution. Which means, if there is a frequency distribution of n classes, with each class defined by its midpoint xi, the frequency with frequency fi, then the variance sigma square and standard deviation sigma is computed by the same formula. The point is that, dear students, here is that the class interval is actually transformed to a midpoint value xi. Okay. Now there is a shortcut method, and then there is a proof for this shortcut method, but we are not discussing this shortcut method here, that proof of that shortcut method here, but it is extremely important that you use this formula. Okay, now why this shortcut method is required? Because it is quite a tedious process to compute the value of sigma square and sigma using the formula what I mentioned so far. So that's why there is a shortcut method, and we encourage that you use this method while solving numerical problems. So what is that, dear students? So for the data set x1 x2 up to xn, that what is the mid values. So how you compute is that we compute the sigma square is equal to 1 by n square, n into summation of fi into xi square I equal to 1 to n minus sum of fi xi, where I equal to 1 to n complete whole square. And that is the way we find that variance, and standard deviation is nothing but a square root of that, where n is equal to sum of all these frequencies. Now let us understand by means of an example, because example will help us to compute this value very clearly. Okay, so first example, what we are going to do is that finding the mean, variance and standard deviation for discrete frequency distribution. And I'm going to place that example in front of you in another few seconds. Okay. As you see, dear students, that we need to find the mean and standard deviation of the following discrete frequency, discrete frequency distribution. So that we need to find that variance also, and let's see how we can compute it. So we need to compute that table. So we need to construct that table. More than compute, construction is the right word here. So let me first show you this table. And dear students, while you will solve this numerical problem, you need to compute the table just like that. Many of you already started doing it. So you see, these are the xi values, and there is their respective frequency. So fi into xi, x bar you already found it out, that is 100. Then x by xi minus x bar, some positive, some negative, but if you make them square, all are positive. Then fi into xi minus x bar whole square you got, and their summation is 640. Now, dear students, how you compute the variance? So the mean we get as 100, and we get the the variance is something like this. Okay, so usage of this formula, that is 1 by 22, because 22 data is given. I equal to 1 to 7. 22 is the number sum of these frequencies, and there is if you look into it, there is 7 data points here, 7 values. and then we compute and we get the value of the variance as 29.09. Now, dear students, so I'm going to show you the next example to finding the variance and standard deviation for continuous frequency distribution. So for that, we need to get the table first. So that will be provided in the example, and that I'm going to show you in the next page. So if you look into it, dear students, that the table, let me first place the table in front of you. So let us find mean and standard deviation for the following discrete frequency distribution. Okay. So following continuous frequency distribution. It's not discrete, it is a typo here. Okay. So for that, we need to compute the table. And we need to construct the table. And the constructed table will looks like this. So these are the class interval, and then from there we get the midpoints. So these are the midpoints. Then we made a square of them. Then frequency we know. Okay, so we know the frequencies. Then you compute Fi into Xi. And then we compute Fi into Xi square. And then we made all these three sums. Summation of Fi, summation of Fi into Xi, and summation of Fi into Xi square. Now these three values will actually help us to compute because of the shortcut method. Okay, and we will get the value something like this. So now I hope you will get a fair idea that why this shortcut method is more meaningful. Okay, so please have a look into it. So we compute the variance and standard deviation as sigma square is equal to 1 by n square into n into summation I equal to 1 to 5 Fi into Xi square minus summation of I equal to 1 to 5 Fi Xi complete whole square. And we compute it further and we get the value as 132. That is the variance, and standard deviation is square root of 132, that is 11.49. So we get the variance and standard deviation as 132 and 11.49 respectively. So this is the way we compute. We are almost done. But the last point, which is very important, and I also raised this point during the discussion of standard deviation and variance. The fundamental question is that why standard deviation is a positive square root of variance. The moment you find the variance by sigma square, then why it is required to have another term called sigma? Okay, so many of you may have this question. So if you look into, I'm going to answer that question. In the calculation of variance, we find that the units of individual observations xi and the unit of their mean x bar are different from that variance, since the variance involves the sum of the squares, that is xi minus x bar whole square, which tells that the variance expressed in squared units with respect to the units of the observations. Correct? So that means what? If we need to, let me first place the point and then let me explain further. Let me read out once more. This is important statement, dear students. In the calculation of variance, we find that the units of the individual observations xi and the unit of their mean x bar are different from the variance, since the variance involved the sum of the squares of xi minus x bar whole square. So at one end you have xi and x bar. Suppose we are measuring the length, okay, length of field, many fields. Okay, but when you find that the variance is nothing but it is involved with the squares of this thing. So that means if we describe the length as meter, this one, we need to describe this as meter square. So meter square means what? It is area. So we are going to find the variance and standard deviation, the method of dispersion from a length, but we are getting the result in terms of area, which is not correct. Correct, no? Because the square of xi minus x bar whole square tells that the variance is expressed in squared unit, that is meter square, which is area. Okay, and that is not very conformal. That is not goes well. Hence, to make the unit of deviation a same scale of the unit of observations, a new term called standard deviation, denoted by sigma, is introduced, which is nothing but the positive square root of the variance, denoted by sigma square. Okay, but for looking at a distribution, either of the variance or standard deviation can be used. But this is the exact justification why standard deviation is required despite having variance, and why standard deviation is a positive square root of the variance. Correct? So to make the unit of deviation as same scale of the unit of observations, a new term called standard deviation, denoted by sigma, is introduced, which is nothing but the positive square root of the variance, denoted by sigma square. So dear students, with this we are done with statistics, and it is I hope you enjoyed the session, and now it is your task to go to the online platform at www.konarclasses.com and start appearing the DPPs. So I will appreciate if you appear 2 DPPs by tomorrow before we start our class, so that we can make some practice tomorrow on statistics. So with this note, I would like to conclude the class for today, unless you have any specific question for me.
Thank you.
Thank you very much.
Thank you.
Thank you.